Yo, what's up? So today, as I kind of have written on the board, we're going to be talking about some physics concepts in calculus today and how they relate positions, velocities, and accelerations. Pretty fundamental concepts of physics, probably one of the largest applications of calculus in another field. So hope you enjoy this. Let's get our thinking caps on and let's begin. All right, so think about what a position is. I'm standing here, or I'm standing here. That is a position, an instance of where you are, right? But the thing with velocity is that I'm going to write velocity as v today. V is actually just going to be equal to the derivative of, and then I'm going to say position as just the POS today, right? Velocity is actually just going to be your change in position, right? So if you've ever thought about that before, your velocity, or sometimes more commonly referenced as speed, there is a difference between speed and velocity, and we'll go over that later when we talk about integration, right? But velocity is going to be your derivative of position, so your change in position. And then you have acceleration is going to be your change in velocity, right? So I'm walking here, right? My position is changing. I have a velocity. But what if I started walking slow and then all of a sudden sped up, right? So yes, acceleration is going to be your change in velocity, which the two of these together means that acceleration is going to be the d squared over dx squared, right, of your position. So, goose, making a lot of noise. So yeah, your acceleration is going to be your second derivative of position, right? So this is a kind of fundamental relationship in physics, right? Describing how your location is changing and how your change in location is changing, right? We can represent this through graphs, right? If you have a position graph, let's say I move forward, a little bit, speed up, and then start moving backwards pretty fast and slow down, right? So your position might look something kind of like a parabola almost, where you start here, kind of move forward, get to a spot further away, and then you start moving back, right? And so when we start thinking about graphs in math and positions and all this, it gets kind of confusing because, you know, on this y-axis, we're not always moving forward. Even though we are moving, our position could be decreasing. So sometimes thinking about your position decreasing can be tricky, right? But it all deals with directions. And in calculus, the direction or sign, values, like positive or negative, of your acceleration, position, velocity are pretty important. They tell us some things, right? And so I'll show you that now. Looking at this parabola, like if this was this would be a graph, it'd be like negative x squared plus something x and then minus something, right? To get this sort of graph. And so your velocity would be equal to like f prime of x, if this is f of x, right? Which would be equal to something like negative like 2x, and then plus, I'll just say like 1 for now, right? Whatever it is. So, and then I'll actually draw this in red on the same graph, right? Your velocity would start right here, and it would just go down, kind of like that, right? It'll go on forever. But if you think about this, your velocity is always pointed down. It always has a negative slope, right? And that slope is going to be acceleration, right? Your derivative. We'll draw that later. But if you think about this, what is happening, and I actually drew this wrong. I'll show you why in a second. We need to have our velocity intersect the x-axis at that point where you turn around. Because if you think about what your derivative is doing, right? If you remember our differentiability video where we talked about, you know, what, or in our tangent line video when we talked about like what the derivative is doing, right here at this point, you have that peak, right? Your derivative is going from positive because you have a positive slope. Think about that. If you have a positive slope, you have a positive derivative. If you have a negative slope, you have a negative derivative, right? But if you go from positive to negative, there has to be a point where that's equal to 0, right? If you remember all the way back to the intermediate value theorem, you can apply that to derivatives too, right? If you go from positive to negative, you have to have hit 0 at some point if your function is continuous. We look at our velocity here, and on this portion, and I'll erase our velocity function here, this portion right here, our velocity is positive, right? It is above the x-axis. And our position is increasing, right? But then here, our velocity is equal to 0. We'll talk more about that later. That's called a critical number. A critical value is where this velocity is equal to 0. X equals something, and that's going to be a critical number. We'll talk more about that later, right? Pretty important thing. But then over here, and I kind of took up my space with an arrow, over here, your velocity is negative. Velocity is negative and your function is decreasing, right? And so kind of trends like this happen throughout calculus, and we're going to use a lot of this stuff later, right? Pretty important stuff. Lastly, I'll draw out the acceleration. We decided that this would be like negative 2x plus 1, our velocity, right? So that means our acceleration would really just equal negative 2, right? Because if you look at the slope of this graph, it's always negative. So we would actually have kind of an x-axis go all the way down here, and I'm kind of out of space, but if you look at this, your acceleration is always negative. That actually tells us something. Remember, acceleration is the second derivative of position, right? And I like this example a lot because either in our next video or sometime coming up soon, we're going to talk about the relationship between functions, their derivatives, and their second derivatives, and what information that gives us about a function. Because I can tell you right now, if you told me that a function's second derivative is always negative, I could give you some pretty interesting information about that function, including the shape, its overall behavior, right? How it opens, if it's above, below the x-axis, right? So I really like the example of position, velocity, and acceleration. It's applicable to other fields, right? Physics, mainly. If you've ever used a car, you see the speedometer, it shows you a velocity, right? If you're coasting at 35 miles an hour, not changing anything, your acceleration is going to be 0, right? And there is a derivative of acceleration. It's called jerk. We don't really care about that here because we don't need to go that far. Maybe in higher levels of physics you will care about that, but we don't really care about that right now. We really only care about function, its derivative, and its second derivative. Second derivatives are pretty important, right? Third derivatives, not so much for right now. But yes, first and second derivatives. So this lesson, although kind of shorter, it introduces a lot of topics that we're going to go over in the future. Again, I also really just love this example of thinking about your change in location as a speed, right? And your change in speed as an acceleration. So in the future, we'll have to think of more things kind of analytically like this and with graphs. So anyways, I hope you enjoy. Thank you for joining me. Hope you learned something today. Goodbye, class.